Okay, welcome. My name is Ola Liddahl. I work for ARM. I think most of you know me already. I'm here to talk about the Scalable software scheduler. Actually, I'm here to talk about scalable software in general. We're just using the scheduler as an example. I thought that would be more of generic interest. So I didn't really know the audience. It seems to be a lot of familiar faces, but let's start with what does a scheduler do? So this scheduler is a work scheduler. It schedules events such as packets, timeouts, notifications from queues to threads. And since there are often many threads, that's an interesting problem. But this work scheduler, it provides parallelism, so you can use multiple CPUs efficiently. And the idea is also to avoid single-threaded bottlenecks and avoid single-threaded performance requirements that you might have when if you're not using a scheduler-based programming model. And Open Data Plane Work Scheduler also provides some additional features such as order restoration and mutual exclusion. You cannot just do unlimited parallel processing. The results might not be exactly what you want if threads just process packets in parallel without synchronization. So the work scheduler, if you have a dedicated networking SoC, you might have a work scheduler in hardware. That's a common feature. If you don't have a dedicated networking SoC, that's where this comes in. So the reason why I designed this scalable software scheduler is to also support those platforms that lack a hardware scheduler. And such platforms, typically server platforms, and if you look at current and future ARM-based server platforms, they have a lot of CPUs. 48 to 64 CPUs seems to be the norm. And that's a lot of CPUs to get to keep fed. And we want to promote the unified programming model on both server and networking platforms. Otherwise, you might end up in a situation where you use like a scheduler-based programming module when you run on a networking SoC. But if you run your application on a server SoC, you might use a very different simplified programming model, and you can't just port your application, recompile it for the networking platform. Basically, you have to rewrite large parts of your application if you have different programming models. So the purpose here is to provide the same programming model efficiently on both platforms that lack and have hardware schedulers, or have schedulers. And some additional reasons for designing and researching scalable software scheduler is actually to solve interesting problems and to understand what those problems, what are required from their solutions. So in the process of designing this scalable software scheduler, I have actually invented a number of interesting solutions, such as non-blocking ring buffers and lock-free, non-blocking order restoration designs. This leads to a lot of fun programming. That's always the best projects. What limits multi-threaded scalability? Why can't you just throw these 64 CPUs onto your problem and it just runs 64 times as fast? You have a lot of shared data in your application, likely. And if you protect those critical regions with locks in order to get mutual exclusion, that creates a single-threaded bottleneck, because only one thread at a time can execute this critical section that's protected by the lock. You often have ordering requirements in different operations or functions. For instance, one example here is the ring buffer, which is a common way to implement the producer-consumer queue. The ring buffer update has a number of steps. There is an acquire step where you acquire slots in your ring buffer, and there is a release step. And these two steps must be executed in order, so to say, that a thread needs to release ring buffer updates in the order that these slots were acquired. Otherwise, the consumer would get an improper view. So this creates ordering problems when you have multiple threads that operate on the same ring buffer. And there are also situations where you might have independent, or you might have atomic operations that have dependencies, and you want these to appear in a more or less atomic way. If you perform one operation, which is itself perhaps a multi-thread safe operation, then you also want to combine that with a separate dependent operation that needs to be performed together. And this, I call this atomicity. It's a very loaded word. Could mean many things. But these different issues with software affects your multi-threaded scalability. And if you look at the diagram here, using the lock-based, but it's similar for all of these problems, basically your system throughput gets limited by this critical section. There's only one thread at a time, which then hands over with some delay to the next thread. And if with some probability, the more threads you have, the more threads will be just spin waiting to get its turn to enter this critical section or perform this update that's ordered. So that's how software design can limit your multi-threaded scalability. And these are not problems you see when you have just a few CPUs, a few threads. But these problems do manifest themselves. I've been running on like 16 CPU systems, and already there, you can see how limitations in software, such as these limitations, affect the scalability, the achieved throughput. Very noticeable. There are also hardware limitations that affect multi-threaded scalability. And most of this has to do with cache coherency. That all the CPUs, they have caches, and these caches are kept coherent. And unfortunately, if a CPU is going to update something, a location, that modified line can only exist in one cache at a time. The CPU needs to, when it wants to write, it needs to acquire the right to modify the cache line. And all other copies are then invalidated, and this CPU has the only instance of that cache line. And this means there are cache coherency transactions. This acquire the right to modify the cache line, invalidate all other copies. Those are messages that are transferred over the interconnect to other caches in the system. Not all caches have to be associated with CPUs. That's why we call them caches. It's not necessarily the CPUs that are involved. And these interconnect latencies, because this talking between caches, talking between CPUs is not instantaneous, that contribute to the scalability bottleneck as this modified cache line is being transported around, or the right to it is being granted. The question you can ask, why don't you normally see this problem in normal single-threaded code, is because when you write to a cache, when you perform a normal write, a normal store operation, that can complete in the background. If you have a cache miss, if the CPU needs, or the cache needs write permission to the cache line, the software doesn't see that because it all happens in the background, in the load store unit and in the cache of the CPU. So all the interconnect latencies are hidden from software until you perform too many stores and you fill up your internal queues. But normally, that's not a problem. You also have some aspects of hardware that is of interest to multi-threaded programming. You have atomic read, modify, write operations, such as compare and swap. They're basically synchronous operations that cannot complete in the background. The reason is that they return a value. That value may depend on, for instance, if the CPU managed to get this write access. And it also, if you could perform a compare and swap, maybe, as I said, there is a compare. Maybe this compare doesn't succeed and the compare and swap operation fails. These aspects of these instructions makes it impossible to complete them in the background and hide the interconnect latencies. Instead, basically, when it's time to retire this compare and swap instruction, or ARM has similar instructions, load store exclusive, the CPU has to wait until it knows that the write actually succeeded and there are a number of scenarios where it doesn't succeed. And this status must then be returned to the application, to software. And modern CPUs do a lot of speculation to speed up things and to hide in these interconnect latencies, for instance, when you have cache misses. But these instructions are more difficult to speculate. They have global side effects, conditional outcomes. So atomic read, modify, write operations, such as compare and swap, such as load, store, exclusive, they are slower, much slower than other instructions. Much more of the latency in the system is exposed to software. And not only exposed to software, but becomes part of the critical, there's sort of a critical region in the hardware. For instance, as using compare and swap as an example, it's normally preceded by a load instruction. You perform some computation based on the result of this load instruction, and then you perform the compare and swap operation. And the latency of this critical section is affected by the interconnect latency, because the load is just a load. The compare and swap is when you actually want to write. And that means that in this critical section, you have to wait for other caches to respond. And if you have a long interconnect latencies, that means your critical section is getting bigger. So you also have critical sections as a part of the hardware design, not only as part of software design. And if you do multi-threaded programming, you need to impose the right ordering of memory accesses. You cannot just write to some flag, and then expect consumers of this data to see the right values. So you have, there are different memory consistency models, but the popular one is called release consistency. And it's suited for architecture such as the ARM architecture, which has weak memory ordering. And in the release consistency, you have these acquire and release operations. When you want to release some update, you perform your normal writes, the releasing store to some flag or some other variable that is this synchronization point that has release ordering. And this operation, this store release, may have to stall the CPU to be sure that all preceding stores are now visible by all other agents, all other caches and CPUs in the system. And that have to wait for other agents on the system on the chip, on the interconnect. That can be a slow thing. And correspondingly, the consumer of such an update has to perform a load acquire or some other acquire ordering operation to be sure that loads from this, that depends on this update, don't see the earlier incorrect data, only sees the new updated data. So this acquire ordering prevents the CPU from speculating loads, from accessing the caches earlier in order to decrease cache miss latency. So this inter-core or inter-thread communication is slower because of this. You have to do this acquire and release ordering memory accesses. And the picture here shows the Moesi cache coherency protocol, which is basically what the ARM AMBA specification uses. And there are a number of states for a cache line. It's interesting that in this Moesi protocol, many CPUs can actually have a cache line in shared state, but there can still also be one CPU that has that cache line in what is called the own state, where it has the right to modify the cache line. This is like a protocol that is optimized for multiprocessor systems. There are other cache coherency protocols as well. So now, based on these hardware and software limitations, I have written down some of the design rules that I derived from the way hardware and software behaves in order to achieve better scalability. You want to separate variables. You have some variables that you read and write to, and you have other variables that might be read-only, you only read from. It often makes sense to put these into different cache lines so that the ones that are read-only can always be cached. It always, of course, depends on the capacity of the cache. Because these variables that are written, if some other CPU writes them, they will be invalidated from your cache. You don't want that invalidation to remove data that you might be accessing that is actually not related. So this is the false sharing problem, that you put too many unrelated things in the same cache line. Or they might even be related in a way, but you don't want your read-only data to be invalidated just because some other piece of data happens to be written. But conceptually, they might be related, but from a pure hardware perspective, if you write one location, you want to be able to have quick access to other locations of data. There is also, if you have multiple locations that you write to, if they're written at different times, far away in time, it makes sense to put them in different cache lines. If you have two locations that you write to basically immediately after each other, it makes sense to put them in the same cache line. It's just one cache line you have to retrieve. And when you perform the first write and the second write, when the second write is performed, that cache line is most likely in your cache because of the first write. But the further away these two writes are, the larger the probability it's beneficial to actually put these two locations in different cache lines. You write to your first cache line, which means that the CPU needs the access, it needs the modified, let's go back to this, it needs the cache line in modified state. And when it performs the write to the second location, some other thread might already have written to that first location and invalidated your copy of the cache line. So then it's actually better for you to perform a write to a different cache line. That increases the scalability. Now you have two different cache lines that can be written concurrently. Basically, the more threads you have, the more you want to spread out your writes. If all your writes are to the same cache line, that cache line becomes a point of contention. So spreading out these write targets over multiple cache lines is part of the design rules for scalability. There are some code sequences where conceptually you might read a cache line, you might read a variable and then just write it immediately after. And this is typically if you have a ticket lock. When you're releasing that ticket lock, you're just incrementing the value of the ticket lock current counter. And you often see code, they do, in this case, it doesn't have to be an atomic increment. It's just read, add one, write back. But the problem here, now when you perform a read, the CPU needs to fetch this cache line in shared mode. Otherwise, you can't return the value of the load so that you can perform your addition. And so that you're not hiding the latency of retrieving the cache line. And also, when you then perform your write to the cache line, the CPU must acquire the write permission to this cache line and invalidate any other copies of that cache line you're writing to. So it's actually better just to, in this case, as a specific case, you cache that value of your ticket, for instance, and just perform a write of the new value without the previous load. This means that the write can complete in the background. You don't have actually to have to retrieve the cache line first in shared mode and then later get the write permission. You can just acquire the cache line in exclusive or modified state. And this can also be done in the background. So that's another small trick that you can avoid some of these cache coherency messages and the latency involved in that cache coherency signaling. there are, related to this one, if you, is another small trick, sometimes useful, is actually the CPU can explicitly prefetch for store to fetch this cache line early if there is a potential for cache miss. So because if you have a potential for cache miss, the CPU normally, if you perform a load and then you later might want to store it, as I said, the CPU fetches the cache line in shared mode, and then it needs to transfer that into the modified state. But if you know you're going to write the cache line, even if you're going to read it first, you can tell the CPU, retrieve this cache line in modified state immediately. So when you actually perform the write, that can be done without any latency. This decreases, from a hardware perspective, this decreases this critical section. This is the time the CPU owns this cache line before it can be passed on to someone else that wants to access and modify the cache line. I mentioned these acquire and release orderings that you need when you transfer updates between CPUs. You shouldn't use them more than needed. In some cases, you can actually perform, even if you perform an atomic update of some variable, maybe this update isn't associated with any kind of other memory updates. Then you can actually perform a relaxed operation, which doesn't have this acquire and release ordering of memory accesses, and it generally is a lot faster. This is what makes sense on ARM CPUs, where you have a weak memory model. If you have an x86 CPUs with a more or less strict memory ordering, all of these barriers are more or less no-ops. But I work for ARM, I don't work for Intel, so I'm telling you what's best for ARM. And again, something that is different potentially between architectures, but also within different architectures, is how deterministic your hardware environment, and also, of course, software environment, but that's a different thing. In some of the SoCs I've been running on, you perform a sequence of two threads perform the same sequence operations. If one starts slightly before the other one, they will end in the same order, because the hardware with memory access is very deterministic. But on other systems, it's not deterministic. Just because you have two CPUs that reach one point in the program in one order, when they reach the next point in the program having done the same computations, that will be in a different order. The hardware is not deterministic. Some cache misses will take much longer for one CPU to serve than for the other CPUs, depending on where those cache misses are being served from. And this creates problems when you have this, for instance, the ordering requirements from software. Because this creates a large probability that if you need to perform these operations in a certain order, for instance, to leave this ring buffer update, for instance, to release in a certain order, if the second thread that supposedly was started later might finish earlier, but it's not allowed to finish earlier. And what can you do? You have to spin. Then you're just wasting cycles spinning until it's time for this CPU to finish this operation that it was performing. And with lock-based code, this is even more of a problem, because then this lock-based region might take much longer than you expect in certain cases. It's not deterministic. It decreases determinism. Also, this indeterminism in the hardware starts to affect the software and makes the software less deterministic. And again, if you have lock-based code, all other threads that want to take the same lock will have to wait. And you want to avoid those dependencies between threads. So, an important data type in Open Data Plane are the event queues, and we want scalable event queues. If you profile some example, you can see that there's a lot of time spent in event queues. actually most of the time. And I have implemented them using ring buffers, which is a very common data type, and with separate head and tail pointers for producers and consumers. And if you have these separate, if when you combine event queues with a scheduler, if an event queue goes from empty to non-empty, we want to signal that this event queue is something that we can schedule from. And when a consumer dequeues from an event queue, and that event queue goes from non-empty to an empty state, we want to signal that this event queue is not of interest to the scheduler anymore. And we have something called scheduler queues for that. But now we have the problem that since we have these separate head and tail pointers, which is common, DPDK ring buffers have the same, a queue can actually be both empty and non-empty at the same time. And I call this the Schrödinger's queue conundrum. And it creates a problem, because how can we tell the scheduler if this queue is of interest when it can be both empty and non-empty at the same time? So we need to reintroduce some state that is shared between the producer and the consumer, so that they have the same view of this queue state, if it's empty or not empty. And this state is a shared counter, and there is a ticket mechanism, basically a sort of a ticket lock. And I have a diagram here of the ring buffer, but basically how you perform the different ring buffer NQ and DQ operations. I don't really want to go into detail here about all the things you do, but basically we have the producer side here in purple. You have head and tail pointers for the producers. For the consumer side in blue, we have the head and tail pointers. And we have some extra shared metadata, the number of events and the ticket counter. And so this is the metadata for the ring buffer. And then you actually have the ring itself in the middle. And depending on how you implement the updates here and how you put the data structures, you actually get rather different behavior. So I benchmarked I implemented this ring buffer with different synchronization primitives. I made a lock-based code, which is the blue one, and I have these, the yellow, the green, and the purple. They're all these basically lock-free implementations with separate head and tail pointers. The question is, with the lock-based code, the lock and the metadata is in one cache line. With the lockless code, again, all of these head and tail pointers are in the same cache line. With this, I call them split producer-consumer and split producer-consumer read-write, I put the metadata in 2 cache lines and then in 4 cache lines. And then I measure the number of, basically the aggregated number of NQ and DQ operations. And on the x-axis, we have the number of threads. So I go from 1 to 16 threads. And you can see that actually the best performance is when you only have 1 thread, because then everything is basically in your L1 cache. But so performance degrades because you need to communicate over the interconnects. The system throughput is affected by the latencies of these cache coherency transactions. But there is a rather big difference. Both the lock-based code and the standard lockless implementation, since they both put all the metadata in the same cache line, they have much lower performance. And the 2 implementations where the metadata is split in 2 or even 4 cache lines, the green and the purple, they get twice the throughput. Just because the more cache lines they have, to spread out your writes to, the better your scalability, because then threads can be writing to different cache lines concurrently. So here you see that there is a ring buffer throughput degrades quickly as the number of threads increases. You can affect that performance how you with your layout, basically, of your metadata in different cache lines. But again, if you have too many threads, the throughput decreases, which is something the scalable scheduler wants to avoid. So you don't want multiple threads accessing the same queue, the same ring buffer, because that degrades your throughput. So the solution here in the scheduler is to use different scheduler queues. You have the blue boxes here are these event queues, non-empty event queues. They are mapped to different scheduler queues. In this case, I have a scheduler group with 2 scheduler queues, and I have 2 threads. And each thread has a list of scheduler queue references, these green boxes. And if you look at the green arrows, you can see that both threads refer to both scheduler queues, but in different order. The first thread, T1, is first looking at the first scheduler queue, and then, if that is empty, is looking at the second scheduler queue. The second thread is first looking at the second scheduler queue, and if that one is empty, if there are no eligible event queues, it will be looking at the first scheduler queue. So this is a way to spread out how the threads look at different, eventually how they access these event queues, these ring buffers, to make sure they're actually accessing different event queues instead of accessing the same one. So I will show how this affects scalability. This is how I implement the scheduler queues. It's not that important. In this case, what you have here on the x-axis is actually the number of these scheduler queues. I think this benchmark uses 64 event queues that are then mapped to from 1 to 16 scheduler queues. So when all the event queues are mapped to the same scheduler queue, and I have, in this case, I have 16 threads that ask the scheduler for work, and if these 16 threads have used the same scheduler queue, they all will try to dequeue from the same event queue, from the same ring buffer. And as we saw on that diagram, performance wasn't very high then. So by increasing the number of scheduler queues, basically we can get a linear performance increase. The more we spread out how these threads, in this case I have 16 threads all the time, the more we spread them out so that they actually work on different event queues, process different event queues, the higher the throughput, basically a linear relationship between the throughput and number of scheduler queues. This is what I call the X factor, how many scheduler queues we spread out the event queues on. So in this example here, I only had 2 threads and 2 scheduler queues, but I could have 16 threads here. So these were some examples how I applied these design rules in order to achieve scalability up to, in this case, basically linear scalability to up to 16 threads. It's not only, but to basically to ensure that different cores access different cache lines and writes to different cache lines, because there are lots of write operations involved here. They need to write to different cache lines, otherwise you can't get linear scalability. That's basically one of the most important metrics for scalability is how well spread out your writes are. If all writes go to the same cache line, you have serious contention. Well, that was all. Thank you. François? But in your case here, if you have 4 writes to different cache lines that are part of some kind of critical section that is then released by ticket lock release, it's the ticket lock release that has the store release operation.
All at
I don't really understand your case here, because if you want these 5 stores to be visible or not visible, and if this region is protected by ticket lock, I assume they are only visible if a thread takes that ticket lock. So it's a ticket lock that creates the atomic view of the data you're updating. Or are these other writes also separate atomic operations? No, but that's why you have this store release when you release the ticket. That's what ensures that they are visible when the ticket is released. Yeah, but with x86, the stores will be visible in the order that they are performed, which makes it possible to avoid barriers. Basically, you don't need barriers in x86. And I know I'm not the x86 expert, so I don't know under which circumstances this ordering is not required on x86. But I thought that on x86, basically stores become visible in the order in which they are executed. But on ARM, I can assure that if you don't have the store release or you don't have a suitable DMB, for instance, the order of observability is whatever, anything can happen. But that also means you need the barriers, and they in order to impose this ordering of when the updates become visible, that has some extra cost. It's not really scalability. It depends on the situation. If you just, but what I was trying to say, if in some cases you might be updating, if you're updating, for instance, some statistics counters, you don't need acquire and release ordering. That statistics counters is just a separate piece of data. So on ARM, that counter update should just be a relaxed atomic operation. No barriers needed. Someone wants back there? No? It's hard to see with these lights in my eyes. More comments? Okay. Thank you.